We are working on the problem of the harmonic oscillator in quantum mechanics. So in class, we started with the Schrodinger equation, and then we worked through, and then we came down to a reduced second-order differential equation, which we then solved by a series solution. So we said that basically our wave function was going to be in this reduced variable y was going to be e to the minus y squared over 2 times a series solution where n goes from 0 to infinity of a n y to the power n. So we focused on this part right here, and we just called it h. So h was the summation a n y to the power n, where these a sub n's are just coefficients. They're numbers. So as we worked through in class, we came up with a recursion relationship where the coefficient with an index n plus 2 was equal to 2 to the n plus 1 minus 2 epsilon divided by n plus 1 times n plus 2. All of that multiplied by I'm sorry, not a sub 0, but a sub n. So then we put that back into the summation, but what we found is that in this form, that summation, that series, is going to diverge. So to keep it from diverging, we set epsilon, or 2 epsilon, equal to 2n plus 1. So epsilon is now equal to n plus 1/2. And we said we defined epsilon to be the total energy divided by h bar times the angular frequency, which now gives us this quantized energy solution of n plus 1/2 times h bar omega. Anyway, so what that leaves us with now is this recursion relationship where a with an index n plus 2 is now equal to 2n plus 1 minus, and what I'm going to call now n prime, plus 1/2 times 2, where I just basically substituted in the epsilon value. But what I wanted to talk about now was the fact that I wanted to explain a little bit more about this n prime. So if I just clean this up a little bit, I get the coefficient a with an index n plus 2, so that's 2n plus 1 minus 2n prime minus 1 over the denominator, and I keep saying a sub 0, it should be a sub n right here. Okay, so now what does this mean? Well, it means that the energy level is now going to set the upper limit on how many different coefficients we have to calculate. And so if we're trying to calculate, say, n up to the n prime up to the value of 4. So basically, what is h sub 4? What is this polynomial going to be? Well, in this case, we need a sub 0 plus a sub 2 y squared plus a sub 4 y to the fourth, and then we stop right there. Because if we went any higher, it would go past this this cutoff that we've created according to the energy. So this cutoff basically in this numerator right up here, sets how far we're going to go in the recursion formula. So basically then we're just going to set a value of a sub 0, and then from there we can get a coefficient a sub 2, and then from that we can get a coefficient a sub 4 and then stop. If we wanted to look at h, the eighth polynomial, then in that case it would be a sub 0 plus a2y squared plus a4y to the fourth plus a sub 6 y to the sixth plus a8 y to the eighth power, and then we would stop right there. But to get these coefficients, again, we've got to start with a0, calculate a2, calculate a4, calculate a6, all the way up to the eighth coefficient. And again, in this case, the coefficients are different. That's going to be different from what it was. So if we go back to the n prime equal to 4, in that case, then we would have to first figure out what a sub 2 is, and a sub 2 would be now a sub 0 times 2 times the 0. Let's see. Oh yeah. So it would be 2 times 0 plus 1 minus 2 times 4 minus 1. Because now the n is 0, but the n prime is always going to be 4 because that's the cutoff value. And then we have 0 plus 1 and 0 plus 2. And then if you work it out, you get a sub 0, and then you'd have minus 8 over 2, so minus 4 a sub 0. What you would get for that coefficient. Now, if we work out the a sub 4, that's going to be related to a sub 2. And now in this case, the n is 2, but the n prime is still 4. So we'd have 2 times 2 plus 1 minus 2 times 4 minus 1 over 2 plus 1 times 2 plus 2. And in that case, we would get 4 plus 1 minus 8 minus 1 over 3 times 4. And you would get an A2, which is basically minus 2 over 12. Or, 2... no, I'm sorry. You would get minus 4 over 12, which would be minus 1/3 A2. Now, since A2 is minus 4 A0, I can write A sub 4 as minus 1/3 minus 4 A0, or 4/3 A sub 0. Now we work the same thing out with the evens. So if we want to get the third polynomial, in that case it would be a1 plus a3y cubed. And then what you would get is you'd have to first work out what the third coefficient is from the first. If you're going to work out a fifth, then that would be a1 plus a3y cubed plus a fifth y to the fifth power, which again you'd have to work out the coefficients from each of those cases. Now again, remember the A3 when we worked out the third order polynomial is not the same A3 when we work out the fifth polynomial, because you're changing n and you're changing n prime, or basically you're setting a new a prime, n prime, and you're kind of bootstrapping your way up through the n index. So anyway, so in the end, we could work these out, and so a standard which is usually set in quantum mechanics is to set a sub 0 equal to 1 and a sub 1 equal to 2. Now when you do that, what you get is h0 is equal to 1, h1 is equal to 2, h2 now is going to be 4y squared minus 2, h3 is going to be 8y to the third power minus 12y, h4 is equal to 16y to the fourth minus 48y squared plus 12, and finally y to the fifth, h fifth, the fifth polynomial in this set is 32y to the fifth minus 160y cubed plus 120 y. So these polynomials are known as the Hermite polynomials, because they are worked out by Mr. Hermite back in the I believe it is the 18th or 19th centuries. And actually, if you look it up on Wikipedia, they have a list on here of the Hermite polynomials, what they're called the first 11 probabilist Hermite polynomials, or more importantly, when they're used in quantum mechanics for to solve the harmonic oscillator problem, then you can have a list. Again, setting h0 to 1 and h1, the a1 coefficient is 2, and then you can work out all these cases, and you keep going forever and ever, depending on what index value you want to use. So actually, I forgot, made a mistake up here. That first order polynomial is 2y. Okay. So here's a list of the Hermite polynomials, and you can actually find you can find these in any textbook, any reference manual on differential equations or polynomials that that you can find. Okay, so now I'm going to stop here, but in the next installment, we'll talk about some of the things, some other characteristics of Hermite polynomials.